Welcome back. Hopefully this will fix the camera issues and be a little bit clearer to see. All right, so in this problem, we were looking at this triangle where originally we had calculated the area of it. And so I'm going to start with the simple example and then translate this to our more general example. So this is what we call B. This is, I think we had 2 and 0 here. And then up here, we had the value of C, and this was 0 and 4. Okay. So we were saying let n equal 4, and n will be the number of rectangles that we have. Okay, and so delta x was going to be b minus a over n, where b is the x component of this of the base, and then the a is the a component of the base, and so it's going to be 2 minus 0 over 4, because n was the number of rectangles that we had. So that gives us then that our delta x is going to be equal to 1/2. So that's the length of each stride as I step along this x-axis in creating my partition here. Okay. I also need the equation of the line that goes through these 2 points that forms the hypotenuse of this right triangle. Um, that'll be the height of the rectangle that we're constructing. And so it should be pretty obvious that I have the y-intercept here, and then I was looking at the slope difference here. So this is going to be 4 minus 0 over 0 minus 2x plus 4, which simplifies nicely to negative 2x plus 4. Okay, so I'm going to plug in each of these. And in class, we talked about having um, each rectangle have a left endpoint. And so for left endpoints, and I'm going to be more consistent with the language here. So for left endpoints, uh, for evaluating our heights, okay, this is the height of our rectangles. Okay. We're going to use xi is equal to a, the place that we're starting at. Okay, so in this case it will be 0, but we may have a point over here, for example, and that's where we started. So it's going to be a plus I minus 1. So if we were to start at I equals 1, then because we wanted to start at our left endpoint, we're really not going to step at all in that first direction, delta x. The equivalent of this would be, of course, is if we let I equal 1 or I equals 0, and then this would be delta xi, and we loop that run. But for the sake of consistency, let's just keep it with I going from the sum going from 1 to n, and we'll adjust our left endpoint. Just for completeness, right endpoint, if I could spell right, endpoint or endpoint apparently, would be xi. That would be a plus I delta x. And again, this I would go from 1 to n. So the difference between the two endpoints calculations is literally just what rectangle value you have. Okay, so let's go ahead and simplify this. A is 0. So we have 0 plus I minus 1 times delta x. But delta x we saw was a half. Okay, so this is really just I over 2 is the rectangle value or the value of the locations here. Okay, and so actually we could figure those out pretty easily. So when I equals 1, okay, then the left rectangle here is at 0. When I equals 2, so delta, I'll say xi equals 0, x1, or x1 equals 0, x2 is going to equal, when I equals 2, I plug that in, 2 minus 1, so it's going to be a half. And then when I is equal to 3, if I plug that in, 3 minus 1 is 2. 2 is going to be I, or delta x, sorry, or xi, x3. It's going to be one of those numbers. It's going to equal 1. And then finally, when I equals 4, 4 minus 1 is 3. So that's going to give me then that x4 is going to equal 3 halves. Okay. So those are the locations of our heights. So our first rectangle is going to be roughly there, and then our second height is going to be from here down, and then our third be from there down, and then our fourth, of course, from there. So this is going to be an upper sum because this is obviously going to be more than the value there. Okay, so this is A1 here, this is A2 here, this is A3 here, and this is A4 here. So we're going to sum up each of these four areas and then use that as an approximation to the actual area under the curve, which we'll derive directly in a second. So plugging in each of these values in, so then the area, the total area, is going to equal the sum from I equals 1 to 4 of y of xi delta x. So plugging in our information here, we have the sum I equals 1 to 4. And this is where, in the sum here, where I was choosing to write the left endpoint with the I minus 1. That way we can be consistent or having our sum always go from 1 to n, whatever n being for the number of rectangles. Okay. All right, so we can plug this in. So we're going to have y of I over 2. So my xi we saw was I over 2. And then delta x we saw was 1/2. So I can actually plug that in. And this is a constant with respect to the sum. So I can actually pull that out. And I'm going to plug in the I over 2 into our equation of the line, which was up here. So doing a couple things at once. The 1/2, the delta x coming out. The sum from I equals 1 to 4. And then again, plugging in here, I have uh, negative 2 times I over 2, which is the xi term, plus h in our case was 4. Okay. And all of this is under the sum. Okay, so don't forget that. So if I plug in each of these I values, I'm going to recreate each of these. Oh, I should say this is not just I over 2. Sorry, this is I minus 1 over 2. Forgot the minus 1 part. So minus 1, minus 1. There we go. Okay, so the first one is going to give me A1 plus A2 plus A3 plus A4 is going to give me here. Okay, so I have 1/2. That's going to be times everything. The first one's going to give me 0 because when I plug in I equals 1, 1 minus 1 is 0. So that's going to give me 0 uh, plus 4. Okay, so that's the first A1, or that's A1, I should say. Um, plus, okay, and then A2 is going to be 2 minus 1. 2 minus 1 is 1. This is 1/2. 1/2 times a negative 2 is going to be a negative 1 plus 4. And then 3 is going to give me 3 minus 1, that's 2. 2 divided by 2 is 1. It's going to be negative 2, so it's going to be negative 2 plus 4. It's going to give me positive 2. I'll keep consistency here. And then finally, when it's 3/2, so negative, it's going to be negative 3 plus 4. Okay, so hopefully that's clear where each of those numbers are coming from. And now I'm going to add 4 plus, this is what, 3, 2, 1, and 4. So 4 plus 3 plus 2 plus 1. So this is 7, 8, 9, 10. Half of that is 10 over 2, which is equal to 5. Okay, so this is the area approximation of the total area, which is 1 unit larger than we know it should be. Okay, so let's recap what we did real quick, and then we'll extend this to the case when we make in a number of rectangles. Okay, so we chose a number of rectangles. We found the base width of each of the rectangles by taking b minus a over n and give us a half. We found the equation of the line here. Sometimes that's given to us. Sometimes we know the height of the function. And this is going to be the height of the rectangles. Since we wanted left-ended points, we're going to stay consistent here. We're going to be a plus I minus 1 times delta x, which reduces to I minus 1 over 2 since a is 0 in this case. And then we went ahead and plugged in each of these areas. So we have base times height. I should say that backwards. Height times base. The base is the constant that 1/2, and each of them are the same, so I can factor out of all of the sum. And then I just plugged in each of the values for I through each of those and computed the result. Okay, so let's then consider what does this look like for the general case. So remember, we're trying to get to uh, the area of a triangle, trying to arrive at least in this, maybe this specific case where the triangle is a right triangle. Okay, so let's just kind of sketch it out real quick. So again, we have B and 0, and this is our point B. And then we have here that our A is at 0, 0, and then our point C here is at some arbitrary height h. Last time that was 4, now this is some h. Okay. So I'm going to consider left endpoint again, just to stay consistent with the previous example. And so this point right here is going to be some xi minus 1, and this point here will be xi. And that's completely arbitrary. You can call this xi, and this would be xi plus 1. Um, that is neither here nor there. Okay, so we're going to do the exact same thing. So delta x, in this case, is going to be b minus a over n. Our a is 0, so we can simplify this a little bit and say that this is just b over n. Okay. And again, the equation of the line will need, so in this case, it's going to be, again, it'll be h minus 0 over 0 minus b times x plus, and again, the y-intercept happens to be h. Simplifying just a little bit, this is h over bx plus h. Okay. Barring any simple mistakes, this is the equation of line that will determine the heights of each of these rectangles. Okay, and so I need to know my xi. So since I'm doing a left endpoint, it's going to be a plus I minus 1 times delta x. Um, for our specific example, a is 0. So we have 0 plus I minus 1. And then delta x again will be b over n. Okay, which I may write x I minus 1 b over n. I don't know if that's any simpler or not, but at least it's another way of thinking about it. Okay. All right. So then I have my base, I have my height. Okay. So my area, my total area is going to equal the sum as I goes from 1 to n. Not f. In this case, we're going to use yi plus delta x, or times delta x. Okay, that's my area total. So if I plug in delta x as a constant with respect to this sum, so I'm going to factor that out. So this is going to be b over n, and then the sum from I equals 1 to n of plugging in yi, which is this fun stuff, into my equation here. I have negative h over b times b over n, I minus 1, plus h. Okay, so this is the x part here, and then I'm plugging in this quantity in for x, and then this is the plus h there. Okay, so you should see that the bases cancel, and I have an h in both of these terms. So I'm going to factor that h out and put it with this guy. So, and then what can I do? I can distribute the piece cancel, and I can distribute that negative sign, that negative 1 over n through. Okay, so I have equals hb, the h coming from both of these terms, over n. We have a sum, I equals 1 to n. The b's cancel. I'm left with negative 1 over n, I minus 1 plus 1. Okay. Now I can use the linear operator properties of the sum here and distribute. So I can distribute this negative 1 over n into each term, and then see what they have left over. So we have hb over 2. No, not over 2, sorry, over n. And then that's going to be multiplied by everything. So then I have a negative I over n that I'm summing over, minus, and a minus sign make that a positive sum of 1 over n, and then plus just the sum of 1. I equals 1 to n, I equals 1 to n, and I equals 1 to n. Okay. Simplifying each of these, I have hb over n This is going to be the sum of I, so the negative 1 over n can come out, and the sum of I is what we're working with here, plus the 1 over n can come out here, and this is just the sum of 1 plus the sum of 1. And so these two should be pretty easy to see. I'm going to add up, uh, this is saying I have n ones that I'm adding all together. So how many am I going to have? I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to n. So both of these are just going to converge in closed form to n. So these are going to converge to n. So both of those are going to equal an n. This is going to be in closed form. It's going to converge to n plus 1 all over 2. Okay, so summing these in closed form is nice and straightforward. So I have hb over n, and I have a negative 1 over n times n plus 1 times n over 2 plus 1 over n times n, and then plus n. Okay. All right, so the n's here cancel, and I'm left with just 1. And I think I can distribute, so I'll do just a little bit more cleaning up. HB over 2 over n. I don't like thinking that n looks like a 2. And then I have, let's see, a negative 1 over n. And it's going to be n squared plus n over 2 over 2n. Well, maybe I should just cancel that n. That would be n over 2 plus, yeah, that might be easier. So this would just be a half. Negative half? Be a negative half. Wait, I just really messed it up. So let me simplify this. Uh, let me kick it from here. So those ends cancel. I don't know why I didn't see that as just a simple simplification earlier. So this is just going to be then a negative n over 2 here, and then minus 1 half. Okay, plus, that looks like what, a 1? And then plus n. So it looks like I can simplify a little bit more right there. So it's going to be n over 2, or sorry, 1 half. So this right here can simplify to 1 half. I'm going to have an n over 2, and I guess those can simplify also to n over 2. So hb over n, what do I have I have a n over 2 coming from these two simplifying, and then I have a plus 1 half. All right. Excellent. And so now at this point, I can distribute everything through, and then I get that this is going to equal hb over 2. Uh, that's not a 2, that's an n over n, and over n over 2. There's, okay, so those can reduce, and then I have plus hb over 2n here. Okay, so finally I have hb over 2 plus hb over 2n. Okay, and now this is for n rectangles. So in the limit then, so as n goes to infinity, this first term is a constant with respect to n. And this term, as n goes to infinity, this will go to 0. And so the total area then is going to equal h times b over 2, which is exactly what we were expecting from the previous warm-up problem. Okay, all right, I hope that was helpful. I hope that made sense with what we were doing with the closed forms. Uh, and just to review this one again, to finalize this. So this was an arbitrary rectangle. I have n of them in here, so this is just the nth one. I know that each base is going to be the same, so I have b minus a over n. The height of each of those rectangles is going to be along this line, so that line is going to be negative b h over b x times or plus h. And my xi with the left endpoint is going to be a plus I minus 1 times delta x, simplifying to I minus 1 b over n. The I minus 1 here coming from the fact that I'm going to start my sum at 1 here. Okay, so plugging in then for xi into my height of the rectangle here is what this is, and then just simplifying and collapsing down, it eventually gets to this relationship here, bh over 2 plus hb over 2n. And then when I let n go to infinity, okay, and then that implies this is a big to do. When n finally gets to infinity, okay, we'll have the exact area again. We recover the exact area, and so this term will go to 0, leaving only this term left, which is the area of the triangle. Okay. I hope that was helpful, and I look forward to seeing you in the next video.